So today I'll be sharing my experience. So these are the contents talking about hardware engineering at a very basic level as introduction. Then we move to the product development life cycle, and then why the hardware design is tough in industry. And also we'll deal with some basics of electronics hardware, then the ECAD tool and how the PCB design flow takes place in industry, as well as an RTM tool we'll see what schematic and PCB layout will be done, and then some of the tests, validations, and standards. These we will talk about, and then career path and job opportunities as a hardware design engineer. We'll just touch on that, and then expectations from an entry level hardware design engineer. We'll also see that. So let's move on. So basically, everything starts from an idea. So everything starts from an idea. So you have some idea and you want to convert that idea into a project. How you get an idea? Assume that you wanted to pump a water from one container to other container using a small submersible pump. So you manually used to transfer the water from one container to other container. So you wanted to do it automatically. So how you do that? You put some submersible water pump inside the water in container one, and then you switch that pump using a relay board in certain intervals of time. So this is your idea. Let us assume like this. And then what you do next? So in order to realize this idea, you will learn about this project. So in learn about the electronics as well as projects, and then you prepare something called as schematics. Schematics is logical representation of your idea. We can say that it's also a symbolic representation as well as the logical representation of your idea. Schematic clearly shows that, okay, what has to be connected where. So once you're done with the schematics, you do something called as design. The schematics is done also during the design, and certain sections of schematics you will simulate if necessary. Say, for example, the power supply to the pump or the power supply to the microcontroller board. You will simulate and check with respect to different loads how the power supply performs. And you decide after using the simulation data, you decide, okay, whether I have to go with this power supply or another power supply. And finally, after doing all this, you go to the layout. For small projects, which does not have so many number of components and also no high speeds and no RF designs, you can do this on general purpose PCB, or always what I would recommend is the actual PCB layout. So once you do all this, you order the prototype. So you get the PCBs, and soldering of these components on the PCB is called as populating the PCBs. So once you populate the PCB, you test it. You test the PCBs. As per your idea, it has to work. Sometimes, I mean, definitely sometimes it won't work. So what you do, you try to debug it. You will try to identify why it is not working, why this section is failing, why the pump motor is not on, why it is consuming so much of power. You start debugging it. So the process is, again, you try to redesign the schematics and then simulate it if necessary, and then do the layout, and then not necessary all the time you do the layout. So finally you will do the layout and then come back to test it again. So this cycle repeats until your idea is in your hand. That is, your idea get converted to a project. I mean, this project, whatever you're having your idea in your hand, is also called as proof of concept in industry. So this is a normal idea. This is a generic process what you follow for a project. Now let us see in industry. So sometimes in industry, I would say that this will not go in whatever you have seen just now. There are certain reasons for that. You have seen only, I mean, you have realized only one of your ideas. There are so many ideas which is clubbed together and made as a product. And these are much more complex than the simple projects. There are a lot many hardware as well as software integrations. And the software development itself is a different area. It's completely a different area. It's very, very important and complex. And you have seen the testing process, right? I have told you like you will test that once and then redo the design and everything. So here the testing will be completely different. And also certifications. You cannot simply design a product by just searching or reading something. You have to adhere to certain certifications. I will just give you an example of how in industry. So this is the schematic diagram of a laptop actually. I got it in internet. So as you are seeing how many components and how the connections are, this is a 32 layer board. You are seeing so many components and interconnections in between them. So it is really difficult for an engineers or a group of engineers to without a process to achieve this. Now let's come back. So how do we do that? By using a process. The simple answer is by using a process. In industry, like you have seen, in here you have seen the idea. You have an idea and then you finally convert it to a project. In industry, it happens like a requirement. Maybe this requirement is your idea. Maybe this requirement is given by the customer, or maybe this requirement is from an existing product. So you take it and you give the computation to them. So it depends actually. It depends on the industry. So once assume that for the first time, we will assume that the customer gives the requirement to us. And then we will take the requirement and we suddenly we suddenly don't tell him that, okay, fine, we will give you a product with this, with respect to this requirement. The reason is what we do something is called as requirement analysis. We don't suddenly give to the customer that, okay, fine, we have whatever the necessary document to make a product and then you will have your product. No. So what do we do in the requirement analysis? We will check whether the customer, the given requirement is feasible and realizable or not. This is very important step. So because when you commit to the customer that you can do this, and if you don't do it, it's a bad reputation to the company as well as to you. So we do the requirement analysis and tell the customer, okay, I can do this much of requirements. I did not understand this, and this one I have to think of. So finally, you will sit together with the customer and freeze the requirement. This itself will take 1 or 2 months. So once the freezing of the requirement is done, then what we do is research and usability engineering. So I mean, this process is not in all the companies or not in all the industries. This is some kind of generic process. This again varies with respect to industries. Then comes the research and usability. So once we have the requirement in hand, what we do is like we try to identify, do we have any already, we have any products which can modify or which can be given as per this requirement. This is also again a part of requirement analysis. And if we don't have it, we do the research and we do the prototyping. So once the prototyping is done, we again sit with the customer. We again talk to him, okay, this is the prototype. So the customer has to agree that, okay, fine, this prototype is okay for me. Go ahead for the development. So once the prototyping is done, we'll start with the development. Like I said, the prototyping is necessary in industries because it is a proof of concept. Fine. I mean, the proof of requirement. Okay, so these are the requirements, product that you have. This is the prototype you have. Then comes to development. So in this development area, what we do is we consolidate all the prototyping research as well as requirement and develop an actual product here. So we also consider certifications, we also consider standards, and finally we do the development. And then it after the development, it goes to the testing and quality. So we cannot simply give the customer, okay, fine, I have developed a product and you can take it. And you cannot do that. It has to pass certain quality standards. So after that, we'll go for the deployment, and then if required, training and sales supports, and again the maintenance and technical support. These are all the this is also called as aftermarket. So once the product is in the field, whatever the support you give from your company is also called as aftermarket. Now you have seen in terms of product. Now let us break down that product in different sections. Say the hardware part, say the software part, as well as say the mechanical part. So again, it is subdivided. So one of the area is the hardware development. This hardware development, it has got its own process. Again, this need not to be specific to any of the industries. This is again a general process. So what do we do? We'll take the requirement, and what we do is something like architecture of the hardware. So once we come to the architecture, once the architecture is finalized, then what we do, the circuit design. So each module, I mean, in industry, what how we do the circuits is in terms of in with respect to modularization. So we break down the complete circuit into different modules. So then each module is given to different engineers. So what we do is the circuit design for each modules. And once all the modules are done, we'll finally integrate every module into schematic entry. And again, if required, pre-layout SI simulations, signal integrity. These signal integrity is nowadays are using everywhere because the tools are supporting and all that. And it is really good to check whether most of the signals, whatever we are using, I mean, whatever it is required, is properly there or not. And then with properly is adhered to the standards or not. And then the layout design. After all this, after pre-layout SI simulations also, then we'll go for the layout design. So here we'll do the complete layout of the schematic, and afterwards we do the post layout signal integrity simulation. Sometimes in the pre-layout itself, we will not be getting to know, okay, the SI simulation for a particular net is 100% correct or not. So what we do after the PCB, we again do the post layout simulations. We will tune everything to the maximum extent, and then PCB fabrication, then the bare board testing. So once the layout design is done, we'll go for the PCB fabrication. So once we get the PCB assembled, and we go for the bare board testing, finally the board assembly. So here during what happens is, like, if the components are large, say 1000 or 2000 components are there, so the bare board testing is a part of PCB fabrication. If not, if it is less number of components, we'll do it in house. And then finally the board assembly, then the board bring up is really a challenging one, because you have all the components populated on the PCB. Now the board has to work. So I cannot suddenly load the software. First, I have to check the power supply, and then I have to check the function, like different GPIOs, whether it is working. So each sections of the board is powered up and then checked. Finally, the function testing. Finally, the actual software is loaded on the board, loaded to the controller or the processor, and then it will be checked. And the EMC testing. This is really important nowadays, because the product, whatever you have defined, whatever you have done, should function in the EM environment, electromagnetic environment. So this is very important nowadays. So why the hardware design is tough? This is a little bit interesting. So this is the bathtub curve. I think this is not new to you. This talks about the failure rate with respect to time. So assume that you are given certain requirements, and then you started to build the product. So during the building of the product, you will see a lot of failures, and that is still okay. And once, so that is here, that's going to be here. Infant mortality. So during the infancy stage, if you get the failures, that is still fine. Or naturally, it's going to be more. And once it is in the field, it should not get failure with respect to design. Because assume that if the product fails from the engineering point of view in the field, then the customer can take a legal action. So it should not fail in the field at all. So here this is very low failure rate during its lifetime actually. And finally, after the lifetime is out, I mean, once the product passes the lifetime, then it will fail because of the aging and wear out. This is natural. And we are trying to in industry, actually, the people are trying to push this as further as possible, the wear out failures. So the significance of this bathtub curve is, we should take very care while designing the products at this stage itself. So once the product reaches the field, we cannot do anything. So it's again the cost. So if it fails in the field, then we have to do the re-engineering again and again. Okay, now this is the three projects or three products. So all of these are power supplies only, but look how it is engineered. So this is a bigger power supply, which is around 150 watts. And this is a smaller power supply. I say we can say that's 5 watts, and then it is some 3 to 4 watts. This chargers, mobile chargers are. So the advantage of having a better power supply is this can do the function of these two. This bigger power supply, you can use it to charge your phone. You can also use it in place of this power supply to run small motors and all. But these two cannot do its job. Normally, this test bench power supply, this is called as test bench power supply. This is used for testing, but still it has to. I mean, when we are designing this type of power supply, we should keep in mind all the aspects. So he is testing an inductive load, he is testing a resistive load. So different types of loads also we have to consider. This is used only for the mobile chargers, whereas this is generic. Different slides explaining how the hardware process takes place. So what do you think the companies expect in a hardware design engineer candidate when you go for the interview? So when you go to a company as a hardware design engineer candidate, what the companies expect from you? So here are the things. First of all, the engineer, the hardware design engineer, should be familiar with the different components and also familiar with the concepts. And this is a very important thing. I would say not all the concepts, at least something related to what the work he's going to do in the company, what as per the requirement of the company. And then the EDA tools, it's electronic design automation tools. So these are the tools wherein you can do the PCB design as well as simulations also, simulations and all. So the person should be familiar with the EDA tools also, and he should be familiar with the basic circuits. Assume that when you are in a company you're working, so your superior says that okay, do a filter design with this requirement, then you should be able to build a small filter and check it by yourself, and he should be good in theory. So in an interview as well as when you're working, you do not know what you have to apply to get the product in customer, get a product to the customer. So you should be very good in theory in the sense with all the engineering concepts. So he should be capable of building his own setup and perform the required job. This is very important. Assume that you are required to test SPI protocol in an industry, and you do not know how to do it. SPI is very simple. You should know which is master, which is slave, and how the data transfer that happens, and then where to probe, why the chip select, where is the chip select, and these are all available actually. So you are required to test it. So you should be able to know how to build a setup and then perform the test, or how to design it also sometimes. Then familiar with the different equipments. You should be knowing about the multimeters, you should be knowing about the power supplies, you should be knowing about the oscilloscopes, sometimes logic analyzers. So it again depends on the industry. So now comes the EDA ECAD tool. Is there are certain tools which helps you in designing the PCB. Say the flow is like this actually. So first you do a prototype, and then you go for the schematic capture, and then the physical layout. Do the you get the prototype of the layout, and then you test it, and finally if everything is working, then you do the PCB, and then again the documentation. It is also important. So again, if the design and prototype are segmented, I would say, because in a large system, it is really difficult to combine everything, and it's again costly to combine everything and do the PCB. So you do that in sections, and finally you integrate it in the schematic. One such tool is RTM Designer. I would recommend this tool because it is, first of all, everything in one package. It has got the schematic layout, it has got the schematic entry, it has got the PCB design, as well as it has got the PDN analyzer, power distribution network analyzer, and then it has got the signal integrity tool as well. So everything in one package actually, and it is also not difficult to learn. It is easy to learn. This is a very small circuit. It's a 4-channel relay module. So you have a relay circuit here. So this is going to be the final one. So you have the relay circuit here. You have an optocoupler, you have the relay. To drive the relay, you have the transistor, you have the power supply to the external load, and here. So this is copied 4 times here. And then for the optocoupler, you have 3.3 volt regulator. So like I said, this tool is really, really easy to learn. And once you do the PCB, it's going to be like this. Okay, now let me show you the 3D also. You also have the 3D view in this RTM tool, so wherein you can see that okay, this component is sitting on the pad and the pad design is correct. I would recommend you to learn all this. It's not too difficult. Now you have seen this, a relay module, the circuit of the schematic of the relay module. The job, but in my opinion, it is not completely correct, because if at all I'm looking this for the first time, I won't be knowing it. Okay, what are these and where the connections are? You have to check each and every net, and then you have to, okay, this is going here and all that. So in the larger designs, say for example, here in the larger designs, you will not be knowing where and what it is going. So the best way is to put a block diagram. You can see the block diagram here. So this block diagram explains that, okay, this is the processor and this is going here and into which page number. And this is again certain information relating to the timing. And this is the power sequence. So again, in professional terms, these are important. But for smaller projects, it's just waste of time, I would say. Then again, one more question. If a product meets the requirement as per the customer, is the product ready for the release? What do you think? If a product meets the customer requirement, is the product ready for the release? The answer is again yes as well as no. The answer is yes because the product meets as per the customer requirement. It is ready for the release. The answer is no because the product should not come back to us once it is released. So how do you ensure that the product will not come back to us once it is released? So it is through this test, validation, and standards. So there are different types of tests and validations. So these tests are sometimes defined by the customers or sometimes given in the standards. Normally, when while designing the standards itself, while designing the products itself, we'll consider the standards and then we do the product. So some of the tests are like functional tests, environmental validations. So these functional tests are like from the functional point of view, whether the product is working or not to ensure that. Say for example, when I turn on and off, when I make high and low of the GPIO, whether it is happening or not. This is just a one function. So if the functional test is happening, okay, fine, it is good. Then comes the environmental validations. Whenever I'm making high and low of a GPIO, it is in the normal conditions, it is in the laboratory. What if the temperature changes? What if it is in vibration? What if it is in humid condition? So again, whether the GPIO will be high and low at the same level of what it was done before in the lab. So that will be ensured in the environmental validations. Then the endurance test. Continuously, I'm going to make this GPIO as high and given some load, it should withstand, say, for some, in normally it should withstand around 1000 cycles, 1000 hours or so. This is endurance test. Then EMI and EMC compliance test. So whether your product is will function in EM environment with respect to immunity. I mean, in the EM environment, there will be a lot of immunity, whether the product is going to function as expected in the immunity, as well as into emissions also. Emissions, again, the product is not emitting so much of EM radiations to the environment. So that will be tested in EMI EMC. Then FMEA and safety compliances. So this FMEA is called as failure mode effective analysis. So this is a safety from safety point of view. So this product should not harm the entire system. The product should be safe. It's again the safety critical. There are different layers that will be checked here. The reliability test, the MTVF calculations, the warranty calculations, the reliability of the product will be done here. Then if there are any customer specific test, I mean, if there are any specific test the customer asks, we will do it also. So these are some of the standards like ISO, IEC, CISPR, C, etc. So say for example, IEC 6100 talks about immunity test for the power supplies. So when you are designing a power supply, you should consider this IEC 6100, and then you design that, and again you test it with respect to IEC 6100. So when the test passes, then you can release the product. Now, after seeing the entire presentation, I have one question to you. So you can think yourself as a freelancer, and your client gives the requirement for you to design a PCB consisting of 800 to 2000 components in a very, very less time from the scratch. Say you are given very tight schedule. How do you do it? You can put that in the chat box. I'll just continue. You can put that in the chat box and I'll just continue. So this is the career path actually. So whenever you start as a hardware engineer, then you comes as a senior hardware engineer, then become an architect and then system engineer. It depends again on the industries. So these are the requirement for a senior design engineer in one of the company. You can see the schematic entries and generating BOM, the PCB constraint settings and the review. You can see it by yourself. So PCB design, I mean, you should be familiar with the concepts as well as PCB design. But hardware engineering is not just the PCB design. So whenever you're attending an interview, what they expect is, or we should focus on these aspects. Like you should have the hands-on experience to build a PCB project, because sometimes you're put in a situation where you need not to build a you need not to be a part of very big project, but you will support that project by doing some jigs and fixtures for that. So you should be able to put yourself into there and then achieve that. So how the design verification takes place, how the design will be how the design will work fine in the first time. So how do you ensure that the design will work fine? So once you plug in the power supply, it won't blast. So how do you verify it at all? And once you connect to some external devices, the communication will work fine and everything. You should be able to know it. And then the simulations also, if required, like you can do the power supply simulations, and most of them you can simulate without building an actual product itself. So simulation tools are like again LT-Spice, MATLAB, and all that are there. We need not to know at the very deeper level, because once you go to the industry, they'll give you the training. But it is good if you know at the very basic level at least. Then the debugging methods, how to debug a power supply, and then how to debug a microcontroller, a clock circuitry, how to debug a load, whether type of load is applicable to this particular circuit or not, something like that. Then board bring up techniques, like I explained, you have to go in sections and then check each and every sections by giving the power supply, and then finally you can put everything.